Welcome physics students. In today's video we'll be looking at energy transfers within a simple system, and to visualize this we're going to start with a PhET interactive simulator, and we have in front of you the energy forms and changes simulator. So let's enter this. I'm interested in the introduction option from the main menu, so I'll click that, and here we have it. Now the example we're going to look at shortly involves a piece of iron that's been heated up, so let's heat that up. To see that in fact it's working, we can attach a thermometer to our piece of iron. Heat it up and we'll get it nice and hot. There we have that. Let's add in some little energy symbols. So you can see that there's a lot of energy in this piece of iron. Some of it's escaping into the environment and it starts to cool down. I'm interested in this container of water as well. We've got our water there. Let's cool that water down. Yeah, we can cool that as well. We can see the energy transferring from the water. So we've got cool water, and we'll heat our iron block back up. And in the question we're about to look at, we're trying to examine what's the equilibrium temperature reached by a piece of iron when it's placed inside some water. So you'll notice straight away there's energy being transferred from the hot iron block into the water, and they eventually both reach the same equilibrium temperature. So the iron block started hot, it ends up being a cooler temperature. The water started cold, it ends up being a warmer temperature. But in the end, the block of iron and the water both reach an equilibrium temperature. Let's now have a look at how this works mathematically. Okay, let's look at an example. A hot iron bar of mass 2.5 kilograms at a temperature of 120 degrees Celsius is placed in a full 10-litre container of water at 20 degrees Celsius. Find the final equilibrium temperature of the iron and the water. So first of all, let's write down the information we know. So let's have a look at what we have. For the hot piece of iron, we have its specific heat capacity. We have a mass of 2.5 kilograms. We know that it starts at an elevated temperature of 120 degrees Celsius. And when it's placed in the water, it will reach a cold temperature. From the water's perspective, it's starting cold. It has a specific heat capacity of 4,200 joules per kilogram per Kelvin. It has a mass of 10 kilograms. Now that one comes from the original question. Because the volume of the water is 10 litres, and its density is 1 kilogram per litre, we can calculate the mass of the water to be 10 kilograms. The water starts at a cold temperature of 20 degrees Celsius, and it's elevated from the energy from the iron to some unknown hot temperature. Please note that when this system is finally in equilibrium, the cold temperature of the iron will be equal to the hot temperature of the water. They'll have reached an equilibrium temperature. So in terms of energy, this is what's happening. We have a scenario where the energy being transferred from the iron will be equal to the energy being transferred to the H2O. And we can write that as an equation. Now we've made this quantifiable. We've gone from a statement to an equation. This equation states the energy transferred from the iron is equal to the energy being transferred to the water. Let's now substitute in our values and see if we can't find this unknown equilibrium temperature. So this equation shows the energy transferred from the iron, its mass, its specific heat and its change in temperature. And this shows the energy transferred to the H2O, the water, its mass, specific heat and its change in temperature. So as can be shown, from the iron's perspective, the change in temperature is its hot, take away its cold. And from the water's perspective, the change in temperature is also its hot, take away its cold. These two temperatures are in equilibrium. As the iron cools to an equilibrium temperature and the water rises to an equilibrium temperature. Let's now solve this equation. Let's simplify this statement by multiplying our numbers together. And at this point, we want to expand our brackets. Okay, I'm now going to group my like terms. Numbers to the left, pronumerals to the right. I've added my 840,000 from the right hand side to the left hand side. And likewise, I've added my 1,125t from my left hand side to my right hand side. Let's now simplify these numbers. I now have a single number on the left hand side and a single pronumeral on the right hand side. All I have to do is divide both sides by 43125 to find out what the unknown equilibrium temperature is. So there we have it. The equilibrium temperature of the hot piece of iron and the cold water, when joined together, is 22.6 degrees Celsius.
You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.